Welcome to the kickoff event for the Philadelphia Software Localization Meetup, sponsored by MTM Linguasoft, made-to-measure language solutions. The talk for today is entitled Encoding Nightmares and How to Avoid Them. For more information on today's talk, please visit our Meetup website at www.meetup.com/Philadelphia-software-localization-meetup. The plan of our talk today: first, we'll be discussing exactly what encoding nightmares are in localization projects. Then we'll talk in a little bit more detail about character encoding in computing environments and what led to the modern Tower of Babel in the 80s to early 90s, when it became very difficult for people to share documents and communicate across national and linguistic boundaries. Then we'll talk about the rise of Unicode, the solution for allowing people to communicate in many different languages in different computing environments. Then we'll talk about rules of thumb to avoid your own character encoding nightmares in localization. And then tricks of the trade, ways that you can deal with problems that arise. Finally, for discussion, we encourage you to visit our Meetup website. So what are character encoding nightmares? Well, we all deal with them in some way, shape, or form. The most common way we experience them is in viewing website content that has not been properly encoded. This first example, a Taiwanese university, the coding was not properly set either by the author of the web page or perhaps in the browser, maybe trying to force some other particular character encoding. And instead of seeing the Chinese characters, you see these garbage characters we have here. Our next example is this Bhutanese government website. Their native language, Dzongkha, was not properly encoded and is here shown in Windows 1252. Bhutan is known as the happiest country in the world, but in this particular situation, they're not very happy because no one is able to read the content properly without at least properly selecting the content, as you see in this next slide, selecting the proper character encoding so that the Bhutanese content will display properly. Now, if character encoding issues were only related to viewing already produced content on the web, and they could be solved as simply as changing the character encoding in your browsing, these really wouldn't qualify as nightmares. Where it gets much more difficult is in the process of localizing your software or web content. If character encoding is not properly defined or set in the course of your workflow, it can lead to actual data loss and corruption of your documents to the point where retrieving that data can become difficult or even impossible. So in localization projects, character encoding nightmares can lead to confusion between different members of your team when they're finding documents are not displaying as they should be. It can lead to missed deadlines when you have serious data corruption problems or display problems as you work to figure out how to correct them. It can lead to software bugs, as occasionally character encoding issues can make it difficult for scripts such as PHP to run properly. You can also have data in your databases corrupted, and it can lead to embarrassment to your clients when you don't have software that's working properly, or you have a website or document that is not displaying as it should. We all know that computing is based on binary language, that is zeros and ones, also known as bits, that are strung together to make up characters, words, sentences, computer programs, images, and videos that we see. The bits are typically grouped into groups of 8, known as bytes. A byte allows a total of 256 states to be represented, depending on how those zeros and ones are combined. So to store and display text in various languages and computers, character encoding schemes are necessary. These link specific letters and numbers to specific sequences of zeros and ones. In the early days, computing was being done in the English language, and the first character encoding scheme was the ASCII character encoding scheme, which set specific sequences of zeros and ones for the letters A through Z, numbers, and associated punctuation. Now, since the English alphabet has a relatively small number of characters compared to other languages, only 127 distinct binary numbers were necessary. They could do this with 7 bits, even though typically in computing environments, information was stored in 8 bits, also known as a byte. So the ASCII code page, part of which you see to the right, was actually in 7-bit language. The 8th bit was often left empty or stored as 0. It wasn't needed. European language, however, needed more space. German, French, and other languages with various accents, tilde, umlauts on top of their letters simply could not store all of the characters that were necessary in those 7 bits of the typical ASCII character encoding scheme. So an 8th bit was used, the full byte, allowing them to store 256 different characters. So a number of different character encoding schemes were developed using 8 bits to store European languages. So although 8 bits was adequate for European languages like French and German, it simply wasn't enough to store the variety of Asian language characters, including Chinese, Japanese, and Korean. In Chinese, you need to know at least 2,000 characters to be considered basically literate, and more than 40,000 are in common use. Japanese uses at least 2,000 of the Chinese characters and mixes that with its own phonetic scripts. Modern Korean also makes use of Chinese characters, especially in their names, so they all have a need for much more than 256 characters. So the solution for Asian languages was to use more than a single byte, or 8 bits, of information to store their characters. They designed what were called double byte character encodings. They used 2 bytes, or 16 bits. The total number of different possible entities that could be stored within 2 bytes is over 65,000. So that gives sufficient room to store the variety of characters used in the Asian languages. Chinese, Japanese, Korean, all developed their own encodings. And in Chinese, of course, you had the mainland China, which used simplified Chinese language. And in Taiwan, they also had their own standard for traditional Chinese characters that were used. So as more and more countries began to use computing, developing their own language character sets, the number of character encodings available worldwide began to explode. In fact, you even had countries which had more than one character encoding for a particular language. You can see a number of these character encodings here on this slide. So, with the rise of personal computing in the 1980s, it became very difficult for documents encoded with different character encodings to be shared across national and linguistic boundaries. This came to be known as the Computing Tower of Babel. You could have the same sequence of binary digits encoding entirely different characters. In some cases, especially if a document was shared, for example, originally designed in a Western country and sent to an Asian country, it could be entirely unintelligible at the destination country. It was also difficult, as many academics learned, to create documents containing multiple languages, because the character encoding simply could not support that wide variety of characters that might be necessary. And double byte encodings increased the likelihood of having different types of encoding problems when it wasn't even clear when a particular character encoding began or ended. So ultimately, people began to experience character encoding nightmares. Now, the nightmare scenario is more than just not being able to read a document on the web, changing your browser encoding, and being able to go on with your life. The nightmare occurs when documents that you open and save with the wrong character encoding can be changed permanently. Data may be lost irretrievably. So it was time for computer scientists to find a solution to this problem. With the rise in global trade, exchanges between universities and academics across the world, it simply wasn't feasible to continue with so many character encodings and no standards for what particular bit sequences led to what particular character. So they came up with a global unified solution to character encoding that was supposed to end the Tower of Babel problem. A big enough encoding table for all the world's characters. Any linguistic symbol, any particular character would have a unique defined code point that was stored and shared in a universal standard. This Unicode ultimately has a capacity for more than 1 million characters. The Unicode standard is managed by the Unicode Consortium. It's a nonprofit corporation with global members from industry, government, academia, and other NGOs. They approve new characters for registration in the official Unicode standard, and they work closely with other standards bodies, including the W3C for the World Wide Web and the ISO. The Unicode standard is a set of characters, not their glyphs or their appearances. I'll go into a little bit more detail about that later in the presentation. It's organized into 17 planes, each plane allowing for a total of 65,536 characters. It starts with what's known as the basic multilingual plane, which is the most actively used and it comprises most of the characters in use globally. It includes a number of other planes, including one specifically for emoji, known as the supplementary ideographic plane, and a number of private use planes. There is plenty of room for growth. Again, the standard can hold more than 1 million characters, and fewer than 10% are currently in active use. The Unicode standard is not a specific character encoding. The standard links a particular character to its code point. The code point is a 4-byte binary number that's written out in something called hexadecimal format. It doesn't define the specific set of bits that encode the character. That's left up to the specific Unicode character encoding, maybe UTF-8, UTF-16, or UTF-32. As of the spring of 2017, the most recent version of Unicode standard was version 9.0, released in June 21st of 2016. That version added exactly 7,500 characters, bringing the total used in the Unicode standard to 128,172 characters. Again, that's not even 10% of the capacity of the Unicode standard. Some of the additions, including Osage, a Native American language, Nepal Basa, a language of Nepal, Fulani and other African languages, Tangut, a major historic script of China, and 72 new emoji characters. So it's important to note that Unicode is still not ubiquitous. Pre-Unicode encodings that led to the modern computing Tower of Babel are very much still in use. You have older operating systems which use other encodings, popular applications including Microsoft Office products like Word and Excel. And even within the Unicode standard, it's important to note that you can still have character encoding nightmares if you're not paying attention to what specific version of the Unicode standard encoding you're using. And we'll explain that a little bit. Now that we've had a basic introduction to the issues involved with character encoding, we're going to discuss 4 rules of thumb for avoiding your character encoding nightmare. First, limit the number of applications that you use during your localization project. Every application in your chain of translation and production has the potential to corrupt the character encoding. And certainly make sure that nobody involved in your team actually opens a file just to take a look and see what's going on. They may inadvertently save it with an improper encoding and actually corrupt your file. Second, make sure you're using the UTF-8 character encoding scheme in your localization projects. For websites and mobile applications in any language, it's almost always the right choice. Now, occasionally you will encounter resources that are using different encodings, such as UTF-16, UTF-32. Make sure you're aware of this and you use tools such as IconV or similar conversion tools to convert the encoding back to UTF-8 so you don't end up with your own encoding nightmare. Third, know your metadata. Numerous file types, including HTML, XML, Photoshop files, and other application files, allow you to declare the character encoding in metadata at the top of your file. Now, just because you see a particular character encoding listed in a file, it doesn't always mean that that's actually what was used to encode it. But as long as you're maintaining your workflows properly, it's useful and it helps applications understand how to render files properly. Finally, know the difference between characters and glyphs. Technically, the Unicode standard only encodes abstract characters. Characters can be thought of as the base shape, while the glyphs and fonts are particular appearances of those characters. Just like you see the different renderings of the letter A to the right of the text on this slide. Now, this distinction can be important when you're diagnosing a character display problem, but the boundary is sometimes fuzzy. The letter A with umlaut on the top, for example, is actually a complete character with its own unique code point, but it can also be stored as two individual characters with their own code points, which are then combined in display. Now, you have to be aware of the character differences with glyphs, because occasionally you'll have a display problem that you may think is a character encoding problem, but it actually has to do with a font not having the appropriate glyphs to display the necessary character. So again, understanding this distinction can help save you time. Now that we've gone over the rules of thumb for avoiding problems with character encodings, let's talk about some additional tricks of the trade, how you deal with issues that come up during your localization workflow that could eventually lead to a character encoding nightmare. But again, here are some tricks to avoid those in the process. First and foremost is to make sure you check and convert character encodings to UTF-8, for example, at every step in your workflow. When you receive documents or files back from a translator you may be using, make sure that you check the encoding before using the file to make sure that it's maintained its standard. There are a number of utilities available across platforms in Unix and Windows and Macintosh environments that will allow you to check the encoding and to convert it if necessary. It's also possible to check large amounts of files in a single folder with batch type checks. Another issue that can often come up when you're dealing with UTF-8 files is if you send a file out for someone to translate for you, they send it back, the file may still technically be in UTF-8, but it's a slightly different flavor of UTF-8 known as UTF-8 with BOM. BOM, B-O-M, refers to the byte order mark. It's essentially a signal to the receiver of the message, the application, that the string is a Unicode string and that it's encoded in UTF-8. Now, this can be appended to binary strings by otherwise text-neutral applications like Windows Notepad. Now, these additions of this byte order mark at the beginning of the string can actually lead to problems with particular application environments, programming language environments, such as PHP, where often you won't even be aware that byte order mark is at the beginning of the script, but it will prevent the script from running. Now, occasionally you might see this strange series of characters in a text editor, as you see in the image to the right of this text here, especially if the encoding is also misinterpreted as something else such as Windows 1252. Now, it's important to use editors such as Sublime Text or the Icon-V tool to convert your files into straight UTF-8 before you use them in a programming environment. Another important trick of the trade is when you're dealing with spreadsheets, which are often used for exporting content from various CMS systems. Often, those content exports appear in CSV, comma delimited files, and are used in Excel to manage the translation. Excel often mangles character encodings within CSV, and you'll find if you're not careful that you wind up with corrupted files that need to be sent back to the translator or completely redone, again, depending upon the particular language that you're using. A trick, a very important trick, is to use something like Google Docs Online or a Macintosh environment to open the CSV and save it as an Excel file before you use it in the MS Office environment. Once you're finished with the file, you can upload it again to Google Docs, save it as a CSV file, and then send it on to the next step in your workflow or back to your client. For additional tools, please see the discussion section on our Meetup site. And if you have any of your own suggestions, we welcome you to add your own. Questions, tips, horror stories of your own? Visit our Meetup website at meetup.com, Philadelphia-software-localization-meetup. Thank you.